So welcome back again. Yesterday we talked about theorem on isomorphism, and we saw that if there are two groups G and G bar, and there is a homomorphism from G onto G bar, then G, the quotient group of G uh, with the kernel of F is isomorphic to G bar. Okay, and this G bar is nothing but f of G. Okay, if F is a homomorphism onto homomorphism from G to G bar. So this is what we have seen. So in order to prove that there is some group G is there and G bar is there, uh, then there is some quotient group. Suppose this is K. Okay, G by K. This is isomorphic. We need to find what? We need to find a map F from G to G bar, which is 1, 1, 1 to 1, and onto as well as homomorphism. Okay. So this thing we need to find it out. Okay. So this is an important result as we are going to use them in further theorems on homomorphism, or sometimes we say isomorphism. So next result is that let us see what this result says. Next theorem. If H and K are subgroups of a group G, and H is normal in G, then the quotient group HK by K is isomorphic to K intersection H by K. So sorry, H intersection K. So this results hold. Okay. So thing is that we need to prove that there exists an isomorphism from this group to this group, and because on both sides we have a quotient group. So thing is that we need to first verify that H is normal in HK and H intersection K is normal in K. So these things we should verify, and then because we can talk about the quotient group only when we can talk about some quotient group H by some T if T is normal in H. Okay, then only we can talk about quotient group. So okay, this result you may not get directly in your book as a theorem, but it may be in exercise problem. You can see. Let us see how we can prove. Proof. Here, what we have been given. Let us write down. Since H and K, okay, H and K are subgroups. H and K are subgroups of G, and H is normal in G. H is normal in G. Okay. So H intersection K, of course, this will be contained in H as well as K. Okay. This intersection will be contained in H as well as K, and H and K both are not both. This H and K are subgroups, and H is normal in G. So H intersection K will contain the elements common in both H and K by definition, and it is going to be normal in K, and it has a very easy proof you can see, because all elements in this intersection are those elements which are in H always held as in K. And since H is normal in K, so therefore this intersection is going to be normal in K. Sorry, H is normal in G, therefore H intersection K is going to be normal in K. And also you can verify that because H is normal in G, H is normal in G, and you know that H and K is a subgroup. Okay, you must be knowing, if you are remembering that result, that if H and K are subgroups, then their product need not be a subgroup. Fine, if you remember. But this is a subgroup. This subgroups become this H times K becomes a subgroup if Hk equals to Kh. And then using this condition, we proved that if any of H and K, if there are two subgroups of G, H and K, if any of them is normal in G, then of course Hk becomes subgroup. Hk becomes subgroup of G, and since their H and K are both are subgroups of G, so their product will be all those elements from G only. Fine. So this is going to be contained in G, and since elements of H can be obtained from Hk by just taking identity from here. If you take identity here, identity belongs to K. So this is equals to what? This is equals to H. Okay. So of course in Hk, H is there. In Hk, H is there. Okay. And since H is normal in G, so this is going to be normal in Hk also. You can if you wish, you can verify these conditions. Okay. I hope you remember how to prove that a subgroup is normal in a group. So that is a matter of some practice. You can verify it. So you can, I'm writing, you can prove it. H intersection K is normal in K, and H is normal in Hk. You can prove it. For your better understanding, you can prove it. Okay. Otherwise, if you are getting it from here, then there is no problem. So therefore, Hk by K, Hk by H, and K by H intersection K are defined. Defined means so that we can talk about these quotient groups. Okay. Now define a map phi from K to Hk by H. Okay. By phi of K equals to this K belongs to capital K, and can you say something about the structure of element in this quotient group? When we write G by H, so this contains elements of the form GH, where G belongs to capital G. Okay, this kind of set. So here G is nothing but Hk. Okay, so if Hk is there, and in the denominator we have H, so what kind of elements there should be? S times K H. All right, S times K H. Either you can write like this, or Other way also you can write like this. If you are taking left coset or right coset, it depends. Okay, so if you want, you can write here also. There is no problem. So you can write h times k. All right, you can write s times k, and then this h belongs to capital H and k belongs to capital K. Okay, so because small h belongs to capital H and H is a subgroup, so this H capital H times H is going to be equals to H because H is closed. Fine. So elements in this set you can write like this: capital H times K, like this, where K belongs to capital K. Okay. So now you know what kind of elements are there in in this. Okay. So there are so phi of k will be meant to h time hk. K belongs to capital K. Now you know how we are writing like this. Okay. Then phi is a homomorphism. Phi is an onto homomorphism. Not only onto, but one-to-one onto homomorphism, onto one-to-one homomorphism. Okay, so all these things we need to prove. So now we can recall the first theorem. Yesterday we proved that if there are two groups G and G bar, and F is a homomorphism from G to G onto G bar, which is 1, 1 and onto, this is a homomorphism, then G by kernel of F is isomorphic to F of G, or we can say that this is equals to G bar. Okay. So what we need to prove? We need to find a map which is a 1, 1 onto homomorphism from G to G bar. And here also we need to find a map phi which is defined from K to HK by H. And this is 1, 1 onto n homomorphism. Then in that case, what we can say? We can say that K divided by kernel of phi is isomorphic to HK by H. Okay. So what we are supposed to prove? HK by H is isomorphic to K by H intersection K. Okay. So finally we need to prove that the kernel of phi is nothing but H intersection K. That's all. Okay. So first we prove that this phi is 1, 1 onto an homomorphism. Okay. 1, 1 onto an homomorphism. So this we need to prove. Okay. So with this information that H is defined by means of this expression, you can proceed it as follows. Let us write 1, 1 onto 1, 1 and homomorphism. Okay, homomorphism. So first, because once we define some map, we need to prove that definition is proper. I mean to say that phi is well defined. Okay, phi is well defined. Phi is well defined. So for this, we need to take 2k1, and if k1 equals to k2, this would imply that hk1 equals to hk2, and hk1 and k2 equals to phi times of phi of k1 equals to phi of k2. So this is the case. Okay. Then we can prove that this is 1, 1 and onto also. Okay, so let us see phi is homomorphism. First, let us see homomorphism. So for this, let us take two elements. K1 and K2 belongs to capital K. Let K1, K2 belongs to capital K. So phi of K1, phi of K2. This is equals to H K1, K2. And this is because S is normal in G, so we can write HK1, HK2. Because if S is normal in G, then product of two right coset is a right coset. Okay, like this. So, okay. So this proves that, or we can write like this: phi of K1 and phi of K2. All right. So now we need to prove that a phi is onto. To show that a phi is onto, we need to take some element here, and then we need to prove that there is a pre-image in K. Okay. So for this, let capital X belongs to HK by H in this quotient group. Okay. Then X equals to H. And then we can write here HG, where G belongs to HK. Okay, so so this implies that G equals to some H times K. Okay, where H belongs to capital H and K belongs to capital K. K belongs to capital K. Fine. So therefore, capital X equals to here we can write H and then H times K, and this is equals to HK. All right, because small h will be absorbed in capital H. Okay, since H belongs to capital H. Okay, so this implies that this X is nothing but H times K. Okay, this H is nothing but H times K. Therefore, phi X equals to phi of K. This X equals to ये क्या है HK है ना, तो क्या हो गया ये X जो है phi of K के इक्वल हो गया. This is equals to phi of K. So if you are taking any element here, X, capital X here, so we are getting small k in capital K, such that this holds. Okay, so this is onto also. Okay, so what else we need to prove now? What else? You can prove 1, 1. Similarly, you can prove we can verify this phi is 1 to 1. You can prove this. All right. So therefore, so this implies that K K is I think in fundamental, I don't think there was some one kind of thing was there. If you see, just a minute. I think that was a theorem when they requires only only onto. I think, yeah, that theorem was onto only. So we need not to prove this 1, 1. I think we need not to prove this one. Okay, onto only onto is required because we are talking about phi, which should be onto homomorphism. Okay, they are not telling that this is isomorphism, but they are telling that some group is isomorphic to another group. Okay, so that result was the let me write here that result. Yesterday we did that result, and that result was or let me show. I think that was just a minute. Okay, let me show you. I think it was in chapter number 10, not here. In chapter number 10 it was. Okay, so they were talking about okay, this is so this is 2, this was not 1 1. Okay, so there is, if there is a homomorphism phi from G to G bar, so they are talking about into map. Okay, onto they are not talking, so that's why they are writing this is isomorphic to phi of G. Okay, so if there is an onto homomorphism from G to G bar, then this is big. This quotient group is isomorphic to phi of G. Okay, so we need not to verify that that is 1 1, because that may not be 1 1. Okay, in fact that phi or this phi we are not telling that this is isomorphic map. Okay, we are not telling this is isomorphic map, but this is onto homomorphic map. Okay, but if such map isomorphic onto isomorphic map exists, then those quotient groups becomes isomorphic. Okay, not if G, sorry, if F is an onto homomorphism from G to or from G onto G bar, then G kernel of F is isomorphic to G bar. So this was the result. Okay, so we need not to verify that that is 1 1 also. So let us proceed further. Thus phi is an onto homomorphism from hk by h, or we can write from k onto k onto hk by h. Okay, therefore by first theorem of homomorphism, okay, what we have k, the quotient group k kernel of phi, here phi is there. Okay, phi is onto map, is isomorphic to hk by h. So up to now it is clear. Hello, or do you have any doubt? Hello. Hello.
Yes, sir.
ठीक है? Okay.
Yes, sir.
So what we need to prove? In order to prove, we were supposed to prove this result: k h intersection k. This quotient group is isomorphic to hk by k. This quotient group. Okay. So what we need to prove next? Now we claim claim that kernel of phi, the map we have defined, is equals to H intersection K. That's all. Okay. So let us proceed. Let us see. So here kernel of phi is what? Kernel of phi is the collection of all, because this is map from K to this, from K to this group. Okay, this quotient group. So this is a collection of all those elements of K such that phi of K is equals to identity of this. So इसकी identity क्या होगी quotient group की? सपोज G है और H इसमें नॉर्मल है, तो G बाई H की हम बात कर सकते हैं. इसकी आइडेंटिटी क्या होती है? हेलो, H. इसकी आइडेंटिटी H होती है. ओके, सो I think it is clear to you. This identity H is the identity of HK by H. Okay. So let us take some element here, and then we need to prove that that element is also a member of this. Okay, and conversely. So let X belongs to kernel of phi. So this implies that phi of X equals to H. All right. And this X belongs to where? X belongs to capital K. This implies that by definition, phi of X equals to HX equals to H, and X belongs to K. This implies that Hx equals to X. It means what? X belongs to capital H, and X belongs to capital K. So this implies that X belongs to H intersection K. Okay. And conversely, let X belongs to H intersection K, then X belongs to H and K as well. Then this implies that X equals to H. This implies that like this. Fine. So what we have? So thus we have a kernel of phi equals to H intersection K. So this completes the proof. Okay. Similarly, there is another result. You can try it out in a similar fashion, but just there is a change of K and H. Their places, their role has been changed. Okay. Next result is if H and K are subgroups of G and K is normal in G, then HK, this quotient group is isomorphic to H intersection K. So there they have changed the role. They have changed the role of H and K. In the earlier result, H was supposed to be assumed to be normal in G, and here K is assumed to be normal in G. And the rest things are similar. Okay, just we have done in the last proof. So you can try it out. There is another result which is called third theorem of isomorphism. So that result is that if H and K are normal subgroups of G, where G is a group, such that H is contained in K, then the quotient group G by K is isomorphic to G, the quotient group G by H over G S K by H. So this to prove this result, we need to first must be confirm that this is well defined, this quotient group is well defined, this quotient group is well defined. Then this is as a whole, this is also a quotient group. Okay, G by H, that is K by H, has to be normal in G by H. Fine. So for this, we can refer another result, or we can result a lemma. We can write a lemma. Of course, one can try to prove this, in which we can prove that this that G is G by G, H is normal in G. Of course, this is given. That is K is normal in H, and K by H is normal in G by H. So that we need to establish. For this, the result, let me write it down. Let H and K be normal subgroups, normal subgroups of G such that H is a subset of K. Then K by H is a normal subgroup of G by H. So this part we need to establish, right hand side. Of course, because H and K are normal, okay, here H and K are normal in G, so we can talk about G by H. We can talk about this, and K is also normal in H, so we can talk about G by K. So these two done, okay. And K by H, because H is contained in K and both are normal in G, so this is also well defined. That is, H is going to be normal in K. So what remains to prove that K by H is normal in G by H? This we need to prove. And this is this I have put in form of lemma. You can let us try to prove this lemma. Okay. Proof of this lemma, and then after we can use this result to prove that. Okay, that theorem. We claim first that H is normal in K. Okay, because these two things are clear, very much clear. The only thing is not, there are two things which are not clear. One is that K by H, though it is evident from here, but we can have a proof. And then K by H is normal in G by H. Both things need to be clarified here. Okay, so since H is a subgroup of G and K is also subgroup of G, and moreover they are normal. Okay, moreover they are normal. So, and one more thing is given, H is a subset of K. H is a subset of K. So therefore this implies that H is going to be a subgroup of K. This thing. If you have two subgroups, okay, two subgroups of a group, and one is contained in another, then the smaller one becomes a subgroup of the bigger one. ठीक है, H बन जाएगा, इसका subgroup बन जाएगा. It has a small proof, you can try it out. It's not so much. You do not need to give so much emphasis here, but you can try it out. Okay. Now let H belongs to capital H and small k belongs to capital K. Okay, and therefore this implies that K also member of G. This you should note it down. Fine. So now we are trying to prove that K H is normal in G. We want to prove this one. Okay. So since H is normal in G, this implies that K inverse belongs to H by definition of normal subgroup, where K is treated as an element from G, because K is a member of K and K is a subgroup of G. So K is also member of G. And this hold for all H belongs to capital H, K belongs to capital K. So this implies that what? This implies that H is normal in K. So this implies that H by K, this quotient group is well defined. Okay, fine. So now let us see that this is also a subgroup. Okay. First of all, okay. First thing we have proved that because here there are two things are involved, K by H. So now we can talk about K by H, this quotient group. H is normal in G, so we can talk about this also. Okay. Now we need to prove that this is normal in G. Normal in G, it means this has to be first a subgroup of G by H. Okay. So first we prove that K by H is a subgroup of G by H. Then we prove that K by H is normal in G by H. Okay. Now next claim, K by H is a subgroup of G by H. Fine. So we have two step test and one step test also. So let us try it with one step test. We can take two elements from here. Okay. So let us take capital X, capital Y from K by H. Then X equals to HK1 and Y equals to HK2 for some HK1 and K2 belongs to capital K. Okay. So now XY inverse, this is equals to HK1 and then HK2 inverse. This is equals to HK1 and HK2 inverse. And the product of two right coset is again a right coset. So we can write like this. Okay. And because K is a subgroup of G, so there this product is also going to belong to in K. So this is going to be a member of K by H. Okay. So this implies that this quotient group is a subgroup of G by H. Okay, let us prove that K by H is normal in G by H. Next claim, K by H is normal in G by H. Let T equals to G by H. Okay, to prove H is normal in G, what we need to prove? We need to prove G inverse belongs to H. Okay, like this we need to prove. So in view of this, we need to consider elements from here. Okay, some element from here, that is G inverse. So this G belongs to capital G. So this T we have considered from here. Okay, then we operate with this on element of K by H, and let capital X belongs to K by H. Capital X belongs to K by H. Then this implies that T equals to Hg and x equals to hk. Okay, so now consider T inverse like this. Fine. So T is our Hg, and then we have Hk, then we have Hg inverse, and this is equals to Hg and Hk, and we can write this Hg inverse like this. Okay. So let us see how we can proceed. We can write it like this: GKG inverse. Okay, T inverse equals to GK G inverse. Okay. Now since K is normal subgroup of G, so GKG inverse is always going to be a member of K. Sorry. Here, of course, S is also normal, but here we need to consider K. K is a normal subgroup of G, so GKG inverse has to be in K. And therefore, once we let GKG inverse equals to some, because this is a element of K, so this is equals to some element K1, okay, belongs to K. So from here, Txt inverse, this is equals to hk1, and this is a member of K by H. All right. For all T belongs to G by H and X belongs to K by H. So this implies that what? K by H is normal in G by H. So this completes the proof of this lemma. Okay. So now you can try to prove this result. This result you can try to prove with the help of this, because now you know that each quotient group involved here, they are they are well defined. So now you can talk about this. Okay. So you can define a map from G by S to here, or G to G by S to K by H, and then prove that there is a onto homomorphism, and then use the first theorem of homomorphism to prove that they are isomorphic. Okay. So you can try, or I will let you, I'll explain in the next class tomorrow.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.